Hello everyone, I'm Caleb and welcome to Wattage Wisdom, where we believe that anyone with the right motivation and internet access can become an expert in any field they desire. In this video, I'll be going over some more vision-specific applications that will allow you to build a more effective image recognition and classification networks. And if you enjoy the content we've put out so far, I would ask that you please like, subscribe, and shoot us an email with topic suggestions for future videos. So in our previous videos, we've covered the development, accuracy, and training time considerations for all standard architecture neural networks. Now, we'll move on to covering two different types of visual network structures, the Convolutional Neural Network and Siamese Neural Network. Both of these networks are commonly seen in the world of computer vision. However, they also have a wide range of other applications. Convolutional neural networks have recently gained popularity in language processing, translation, and speech recognition models, with even Facebook basing their speech recognition technology on a convolutional neural network. Siamese neural networks, on the other hand, utilize a convolutional neural network as part of their architecture and are oftentimes employed for applications like facial or signature recognition. While this video will largely focus on these networks' use in vision applications, the concepts and techniques explained here can easily be transitioned into other areas. So with this short intro, now it's time to dive into these powerful network architectures and their implementation. We will start by talking about convolutional neural networks and how they can serve as a portal between our machine and the visual world. A convolutional neural network is essentially just a set of filters that an image is sent through before sending it to the fully connected layers of a network. These filters are meant to extract features from an image and can detect things like horizontal and vertical lines, and further into the network, these filters begin to detect much more complex features or patterns embedded within an image. The cool thing about a convolutional neural network is that the inner workings of these filters and the features they detect aren't specified by the designer. Instead, these filters are actually learned by the convolutional neural network during training, as these convolutional layers learn what features are important to extract from an image so that it can be properly classified. Say, for example, you were building a model that was designed to classify house pets, like dogs, cats, and rabbits. Your convolutional neural network would likely learn to extract features relating to the ears of those animals, as it is a helpful way to differentiate between the different types. So as a basic overview, you can just think of a convolutional neural network as a set of learned filters that the image is sent through before it reaches the fully connected layers. This causes the unique features of the image to come to the forefront and allows the network to now learn based off the features of an image as opposed to the image themselves. The structure of this network can be seen in the picture, where the original input image is run through a convolutional layer, followed by a max pooling layer, and these similar layers are again repeated before flattening the image, as we talked about in a previous video during our coverage of input processing, and then finally sending the feature extracted image to the fully connected layers. This structure of having a convolutional layer followed by a pooling layer is quite common, and since you can stack convolutional layers on top of one another, this structure is usually repeated multiple times so more complex features can be outlined in the image. So now that we know the basic structure of a convolutional neural network, we can move on to talking about these new layers in the convolutional neural network and how they operate. So the main layer in a convolutional neural network is, of course, the convolutional layer. This layer is what sets the filters that extract the features from the image and can easily be employed by using the layers.conv2d as seen in the example code. The arguments for this layer are as follows. The first number specifies the number of output filters to be applied in the convolution. In my example, I have the first convolutional layer set at 32 filters and the second set at 64. The second argument specifies the kernel size. I have the kernel size for both convolutional layers set with a 3x3 kernel. The image in the bottom left will help us understand how a convolutional layer works. You can imagine the box on the left is the whole image, while the yellow box inside of it is the kernel. And inside this kernel, we can see little red numbers coinciding with the multipliers of the convolutional layer. What happens then is these multipliers will be applied to their respective pixel in the kernel, and the resulting values will be summed up equaling the new convolved feature. The kernel will then shift to the right by 1 pixel and will repeat this process. The kernel works its way left to right and top to bottom until the entire image has been ran through the filter, resulting in a newly convolved feature. As you can see in this example, the convolved feature ends up smaller than the original image. This shrinkage is because the convolutional layer can only fit so many possible kernel positions inside the image. This can also be seen in the model summary of the example code, where the first convolutional layer shrinks the output from 32 by 32 to 30 by 30. This is where the third argument, padding, comes into place. What padding does is it essentially lines the edges of the image with a border of pixels that all have a value of 0. This retains the shape of the image without affecting its features. By default, padding is turned off. However, by passing the optional parameter padding equals same, you can add padding and keep the output size the same as the input. Padding was added on the second convolutional layer of the example code. And you can see in the model summary that the output of this second layer is 15 by 15, which matches the input size that was passed to it. Overall, padding is recommended as it can help preserve the spatial dimensions of the feature maps and can improve the performance of the model. The other layer used in the convolutional neural network is the pooling layer. The pooling layer reduces the spatial size of the convolve feature, which decreases the computational power required to process the data and ultimately saves time. Basically, it shrinks the image but retains the same features. There are a few different types of pooling layers that can be used. Max pooling returns the maximum value from the images covered by one kernel, while average pooling returns the average of all values covered by the kernel. In the example code, I chose to go with max pooling as it intrinsically performs noise suppressant, because it only returns the max pixel value so it can discard noisy activities altogether, and is therefore usually more effective than average pooling. There are a few parameters for the pooling layer, but the most important is the pool size or kernel size. I have mine set to 2 by 2, meaning this layer will take the first 2 by 2 square, find the max pixel size, and discard the rest. This can greatly reduce the size of your image. We can see this in the first pooling layer in the example, as the 30 by 30 image has a max pooling layer applied to it, and the resulting output image is 15 by 15. This reduces the number of pixels in the image from 900 to 225, essentially shrinking the image to a quarter of its original size. So when we think back to the convolutional neural network structure from the previous page, we know that the image will begin to shrink as it travels through the network. Typically, as the image shrinks from pooling, we can afford to add more filter outputs to our convolutional layer, therefore being able to extract deeper features. And of course, at the end of your convolutional and pooling layers, remember to flatten the image before sending it to the fully connected layers in your network. So this is a basic overview of the structure and implementation of a convolutional neural network, which is primarily used with images for feature extraction. The next network we'll talk about, a Siamese neural network, actually contains a convolutional neural network as a part of its structure, which we'll see a bit later. So the basis of a Siamese neural network is that it is used to compare two sources of input data and then output a prediction if the two images are of the same type. This is different from traditional machine learning models, which take in only one input and try to classify it to a certain category. Say, for example, we constructed the Siamese neural network on the right. Here, we would feed the network two inputs, say these two images of a tiger, and the network would try and figure out if the two input images are both of the same type. With this different type of operation, Siamese neural networks present a few unique benefits. First, these networks are great for applications where you only have a small amount of training data, as only having a few images per class is enough to recognize class similarities in the future. Siamese neural networks also enable the ability to predict new classes of data without having to retrain the entire model. This makes them perfect for things like facial recognition or signature verification, where you only have a few inputs of someone's face or say their signature, and that can allow a machine to recognize them in the future. The basic structure of a Siamese neural network is one that contains two identical subnetworks, pictured here as H1 and H2. Each of these subnetworks process a different input sample and output a feature vector. This process is also known as encoding the inputs. From there, the feature vector, or outputs of the two subnetworks, are then compared in a final layer, or layers, seen here as Z, which generates a prediction on whether the two images are the same or different. This is usually fed through a sigmoid activation function at the end, which just returns a probability between 0 and 1 of the two images being the same type. So in a slightly deeper sense, a Siamese neural network finds the similarities between inputs by comparing their embedded feature vectors. Now note that it is critical these two subnetworks are absolutely identical, meaning that they have the same configuration, parameters, and share the same weights. However, with the stipulation that the two sister networks are identical, there are many different ways a designer can choose to generate and compare these two feature vectors. What I mean by this is that networks H1, H2, and Z can have a variety of different layers, which we will start digging into on the next slide. Here we see a diagram of a Siamese neural network, which includes more detail on the individual layers within the network. As I previously stated, there are many different layers or architecture one can choose to implement when developing their subnetworks. However, what we have pictured here is one of the more common implementations of a Siamese neural network. As we can see, these two identical subnetworks start off using primarily a combination of convolutional and pooling layers to extract meaningful features. After that, the input is then flattened. This entire process is known as encoding the input, as it takes an image, pulls its features to the forefront, and creates what is known as the input's feature vector. Now these two feature vectors are then compared in the final layers for similarities so a prediction can be generated. There are multiple different techniques one can use when comparing these two feature vectors. You can add them, subtract them, concatenate them both, feed them through more fully connected layers. Basically, you can use many approaches to compare them, but the basis of this comparison is on the Euclidean distance between the two feature vectors. So this means the goal of the two sister networks, and a Siamese neural network as a whole, is to produce minimal distance between two feature vectors that are of the same type, while also maximizing the distance between two inputs that are of different classes. Thinking about our example on the last page, if you fed the Siamese neural network two pictures of tigers, you would want the feature networks to be very similar, or close to one another. Well, if you fed it one picture of a tiger and one picture of an elephant, you would want there to be a large distance between the two feature vectors. So, because Siamese neural networks operate differently than the other networks we have covered, we must develop and train them in a slightly different way compared to our traditional approaches. As I stated earlier, a Siamese neural network can be trained on small amounts of labeled data. However, when feeding this data into the network for training, the input data of a Siamese neural network must be in pairs with a binary label, basically 1 or a 0, that states if the two images are of the same class or not. You must also be aware not to create too much training data when generating pairs with your raw inputs. Say, for example, you have 300 images. Now, a simplified way to find the amount of total pairs you can make is the amount of data squared divided by 2. So this means that you are able to create roughly 45,000 input pairs with only 300 training images. Now say we had 10,000 images to train with. That would correlate to around 50 million input pairs. Needless to say, 50 million input pairs would take an unrealistic amount of time to train your network, and so not only can Siamese neural networks learn off a small amount of initial data, but you also must make sure to use small amounts of input data when developing pairs so that you do not severely increase your model's training time. Another thing I would like to mention is that when developing your Siamese neural network, you can choose to either design two identical subnetworks that mirror one another, or you can use the same subnetwork and just run both of the input images through this network, creating a shared subnetwork. This will ensure that both images are being encoded in a similar process, as they're both being run through the same subnetwork, and having one shared subnetwork can also save memory and computing efficiency as opposed to creating two separate subnetworks, which are identical to one another. Finally, when training a Siamese neural network, there are a variety of loss functions that can be used. Binary cross entropy is a commonly used loss function that measures the dissimilarities between predicted probability and the actual labels of binary data. This loss function is easier to implement in your network. However, to truly unlock the power of your Siamese neural network, you will want to use either the contrastive or triplet loss function, as both of these effectively seek to minimize the distance between two similar feature vectors and maximize the distance between two dissimilar feature vectors, which, as we remember, is the goal of our Siamese neural network. So now we'll take a look at these two loss functions and how they operate while training a Siamese neural network. First, we can see the contrastive loss function. Here, y is the value of the label, so in the way this convention is set up, y will be 1 if the images are dissimilar and the right side of the equation will remain, or y will be 0 if the images are of the same type and the left side of the equation will remain. Sometimes you may see the y convention set up the other way, in which case the equation will have the y and the y minus 1 flipped. Either way, just know that the left side of the equation is the loss function for similar pairs, and the right side of the equation is the loss function for dissimilar pairs. dw is the absolute value of the Euclidean distance between the two feature vectors. This can be seen in the picture below, where the two 0 inputs have feature vectors which are very close, so dw is small, while the 7 and 2 inputs have feature vectors which are far apart, so dw is large. This picture represents a trained network, as dw, also known as the Euclidean distance, is small between similar feature vectors and large between dissimilar feature vectors. Now the last thing to mention in this contrastive loss equation is m, which is the margin. This is a value set by the designer, and it is the minimum distance that we need dissimilar feature vectors to be from one another. So overall, this loss function works by attempting to minimize dw and make the Euclidean distance 0 for two similar feature vectors, and maximize dw, making the Euclidean distance at least greater than the margin m for dissimilar feature vectors. Moving on to triplet loss, we can see that it is similar to contrastive loss, except it contains a third input, hence the name triplet loss. Here, there is a base or anchor denoted by a positive input, which is of the same type as the anchor, denoted by p, and a negative input, which is of a different type than the anchor, denoted as n. Like contrastive loss, the goal of triplet loss is to minimize the distance between the anchor and positive example, and maximize the distance between the anchor and the negative example. This equation works by comparing the squared distances between the positive example and the negative example, and adding it to a margin, which is seen as alpha in the equation. You can see in the picture that as the network trains using the triplet loss function, it again achieves the goal of a Siamese neural network by moving the two feature vectors of similar inputs close to one another and trying to separate two feature vectors that are of dissimilar types. Overall, using one of these two loss functions allows you to get the most out of your Siamese neural network and build machine learning models that can accurately predict if two images are of the same type or not. In summary, we covered a lot of information on convolutional neural networks and Siamese neural networks. And you may feel like we flew by these networks in an airplane and I just told you to look out the window and remember as much information as you can while we quickly pass by. So before you leave, I would like to just leave you with a few key concepts and takeaways from the video. Number 1, convolutional neural networks are used to pull out meaningful features from an image. This allows our network to learn based off the features of an image rather than the entire image itself. A convolutional neural network does this by passing an image through a set of filters where it learns what features are important to classify an image. These networks are easy to implement through the use of convolutional and pooling layers. Moving on to the other network we covered, Siamese neural networks are different from traditional machine learning systems, as they take in two inputs and output a prediction on if the two inputs are of the same class or not. It does this with an architecture containing two identical sister networks, which generate feature vectors that are then compared in the final combined layers where the prediction is made. So that is kind of the basics of these neural networks, which offer powerful results specifically in the realm of vision applications. Of course, if you didn't catch or understand everything in the video, don't worry about it. Just try and remember the key takeaways I talked about and come back to this video if you need a refresher or once you start implementing these networks on your own. As always, thanks for tuning in. If you enjoyed this video, I would ask that you please like and subscribe, and definitely reach out over email with any questions, topic suggestions, or if you maybe have some explanatory videos of your own that you'd like to have featured on this channel. And never forget that with the right motivation and internet access, you have the power to become an expert in any field you desire.